So, hi. Today our talk is about automated error handling at Dropbox. And actually today we have two presenters, myself and my colleague Karoly. So, a little bit about us. So, me and Karoly, we're team members of storage. And myself, I'm general SRE, and Karoly is MySQL SRE. And before joining Dropbox, year and a half, I was working in Yandex, which is a computational partner of CERN, for example. And I was working on distributed compiler infrastructure. And before joining Dropbox, Karoly was working in Booking for 4 years, and he was working mostly on automation of databases. And a little bit, what is a SRE? So SRE, if you played video games before, especially fantasy games, you probably know that there are different classes of characters, like warriors or magicians. So SRE, and if you think that, for example, warrior is software engineer and magician is a system administrator or DevOps, SRE position is perfectly what's in between. It's perfect combination of both system skills and software engineering skills. So let's look what is a Dropbox today. And Dropbox, it's a big scale. So we have 500 million users. We have 200,000 business users. And every day we're uploading 1.2 billion files. And let's take a look what is the inside of Dropbox. It will be just general overview and nothing special here. We have application servers which are actually serving requests from clients. But behind the application servers, we have two types of storage: metadata storage and block storage. And block storage is what actually stores data, like storing user data, storing file contents. And metadata stores, for example, file tree structure, or storing data when a user has uploaded the file. And guess what we will be focusing on today is metadata storage. So what is a metadata storage inside of Dropbox? We are primarily using sharded MySQL databases, and we're using EdgeStore. And we had a keynote from Peter yesterday about Dropbox, and he covered this topic, that EdgeStore is actually a graph database built on top of sharded MySQL instances. And let's think, what is Dropbox again? It's not only about these numbers of how many users we have or how many files we're uploading. From infrastructure perspective, it's also tens of thousands of servers. It's multiple data centers, multiple continents, and it's actually petabytes of metadata and exabytes of raw data. And by raw data, I don't mean only user data. We're storing lots of logs, analytics, etc. So having that size of infrastructure leads to interesting engineering challenges. And main challenge is shit happens. And we have like lots of unknowns. Yesterday, during lunch break, I was telling the story back from the days when I was working at Yandex, that Yandex is a Russian IT company, and I was working in Moscow. And Russia has like main connection to Europe or Finland. And you can imagine that one day, industrial excavator was digging something and actually cut fiber optics between Russia and Finland, and we lost connectivity to the internet for 2 hours. So lots of unexpected things are happening. And we actually have way less engineers than number of servers we have. And that's actually a big challenge. So, and that leads to the interesting thing that having that number of servers being prepared to unknown unknowns leads to interesting challenge, automating stuff. And here I'm going to give the word to Karoly, who will speak about automation.
Thank you. Hello. All right. So, as Max mentioned already, and you heard from Peter as well, that we kind of heavy on automation. But when you say automation, most of the people think about scripting, right? You write a nice bash script, a couple of one-liners, but there's actually much more to that. So the different type or levels of automation, if you wish, is you start with scripting, but then you build up from there. And where we want to be is self-managing servers, because we don't like to work. So we just like to have servers doing the work for us, and we get the paycheck. Everybody's happy. So how do we get there? You start with the scripting, which is easy. You basically tell the computer to do what you would do if you would do the work. It's like teaching your dog to fetch. But the concept, you still need to throw the stick. You still need to tell the dog to fetch. It's still a one-to-one interaction. Translating this to computers, you're still working on one computer at a time. You're still doing one job at a time, and you still just have 8 hours a day. So we somehow need to improve that. And in order to improve that, you can run these jobs parallel, and you can run them remotely. I'm pretty sure you are familiar with Ansible, Fabric. These are all examples of those when you can run Ansible on multiple hosts parallel. Fabric, nice Python tool, does the same thing. We have GSH, which Peter mentioned a nice story about yesterday, how we can break servers with GSH, but it's fixed. But still, you need to be there, right? You're still hitting the enter. So another step forward is to get to an unattended executional time when you actually don't need to be there. Maybe you just tell that, yeah, whenever you have time, run this, and it will be done. By the next day, you come in the morning, you check the logs, everything's fine, website is up, we can still back up all those 1.2 billion files. It's all good. And you can also, if you get to that point, you can also run automatic batch execution. And I'm not talking about one after each other. I'm talking about when your job executioner is smart enough to know that if I put 1,000 server in the queue for upgrade MySQL, it won't actually upgrade the 1,000 one after each other, because it knows that we may not shut down the slave that is being backed up at a time. Or actually we can do 100 at a time, because we have the capacity for it. So you need to know what your infrastructure is capable of, and then you can have your scheduler do the work for you. And then we can arrive to a self-managing system where, based on different conditions, it can be periodic checks, it can be events or signals flowing from your systems, you can react. And that's when the servers are starting to manage themselves. Anything happens, you have a reactive action to it, and the server will just do it, because you have all the decision intelligence, all the rules, or the locking mechanism in place, so you know you won't break your system, and then we can focus on nice things. What is more important, like playing the guitar or Guitar Hero, whichever you prefer. So at Dropbox we have some sort of system like that. It was built not specifically for databases, which is called Nauru. Nauru is a reactive system to alerts. Think about Nagios. You come into work, you check Nagios alerts, you have 300 of them, and you go through the very same process every single day, right? You check if it's really an alert, and you do the same action. Nauru helps us automating this. It has 3 big parts: alerting, diagnose, and remediation. Alerting gets the alerts from Nagios, or our own version of Nagios. The diagnose checks if it's really a problem and how to do it. It returns back a remediation prescription. And if it's possible, it runs the remediate plugin. It may need some human authorization, but we try not to have any action which needs human interaction. So, for example, SH unaccessible alert. We get that every time. What you do, SH to the box. You confirm that, yes, the box is really, I cannot really SH, or you say, I'm in, false alert, and you act or resolve the alert. If you cannot, then you check if the box is really down, you go to ILO, and if it's really down, you deallocate the server. Deallocate for us means that we are sending back to the data center operation engineers, and they're either going to reinstall or repair. The whole process is automated, so we don't really talk to the data center operation engineers. For us, they are just an API. Or now you can reboot the server. Whatever you would normally do, it can do it for you. So it really helps us with a lot of operational work, and it removes the day-to-day hassle of doing the system administration work that we all hate. Like process is dead, restart. Disk is full, rotate the logs, you name it. These are all easy stuff, and we are really happy with it. But as always, there's more. Because not all of the remediation are equal. There are stuff which requires multi-host scheduling, synchronization. Remediation may take hours. So imagine one of the database slave died, recloning it or restore it from the backup may take hours or days. This cannot be run in a simple remediation process. This has to be an intelligent, sophisticated job scheduler which runs it. So we want to have a smarter way of doing things. For that, what we want is through events. So we have something that can say, this happened, something will happen. Deal with it. We need prioritization. And what's even more important, we want a task execution to be more granular, not just a check execute. Because we may need to stop, pause the job, resume if necessary. So what we have now is a local agent which runs on every single box. Every agent actually runs more agents, and they all collect very simple things. Think about heartbeat, think about basic replication status, think about performance data like querying MySQL performance schema or disk I/O. And they are throwing an event with a payload to the event bus. And there is a dispatcher who you can subscribe to as a reactor. And if certain type of events occur that you're interested, you will get a notification, and the reactors can react to it. So even monitoring, collecting of metrics data is done by this, because what we can do with this is we have one single collector, and we can have as many reactors to metric collection as we want. So we can write back to MySQL, so we have local agent, we can write to InfluxDB, Prometheus, whenever. And we can just build a new one and write parallel and phase out the old one when it's done. So based on that, we also want to have more. So taking this idea further, we have Wheelhouse.
Thank you.
And Max is going to tell you how it is built,
So
and
yeah,
what it's doing.
at this point, we had Nauru for 2 years roughly, and yeah, it was pretty useful. We automated lots of stuff. We had more time to write more stuff, and we rolled out Nauru 2 years ago at Magic Pocket, which is the scariest part of Dropbox, which actually stores users' data. But then we continuously were integrating Nauru, and different teams had different requirements or different ideas how to automate their services. And we started rethinking what is the actually like next iteration of auto-remediation framework. And we're starting building that from pieces. That's why we have Lego bricks here. We started building that system from pieces. And first thing is like signals and events. Why do you want to have signals and events? Why don't you use just polling? Because you want to react, and usually you want to react instantly on some changes. And for signals and events, you can have any source of information. It could be just Nagios alerts, and you can just reuse the same logic we're currently using. It could be some specific service health checks, which are provided by third-party software like Hadoop or MySQL. They could provide their third-party health checkers. Or we can have, we actually have time series database, and we're collecting metrics constantly. And based on these metrics, we can create a signal that something is wrong, and we can react on that. Another source of signal is actually human action, because sometimes, yes, it's amazing to have full automation, but sometimes we still want to have a control on what is happening in the system, and we have human actions as a source of event. So next basic brick is event-based finished state machine. If you think about like what was Nauru before, and we presented Nauru 1.5 years ago at SRECon in Dublin, why do we want state machine and why we had that before? Nauru has a pretty simple and straightforward execution logic. It's more like DAG, direct acyclic graph, but FSM is not DAG, it's just dgraph, it's just direct graph. And we want to have cycles in our logic. And actually, state machine provides good mathematical model to model what we're trying to do. And it's actually easy to argue about the correctness of any mathematical model and why it is event-based, because we want reactiveness. We want to reactively make transitions in state machine on some sort of events. And why another good property of state machine, it has steps, and we can resume and suspend on different steps. And it's actually easy to represent any state machine because it's a graph, and that's what we're actually doing inside of Dropbox. We're using just graph viz for representing the current state of state machine, and any SRE can look at current execution of remediation and can understand in which step state machine is right now. And next building brick is a scheduler. Why do we need scheduler? So first thing which scheduler provides is prioritization. Some tasks are not that important. They're just maintenance. Sometimes shit happens, we need to fix production. And that leads to another useful property of scheduler. We want to have synchronization. For example, we want to have a rate limit. We don't trust our software. We don't trust anything. We're paranoid about automation. But we want to have synchronization points. And for example, we want to have semaphores. And we want to rate limit the number of parallel executions of some type. And that's general overview how wheelhouse looks. So on the top is a source of signals. We have sensors, and by sensors we call some sort of alerts or subprograms which can instantly send an event. They're not poll-based, they're reactive. We have human, yeah, we want to have human actions as well. We have old poll-based, and we have old alerts from Nagios. Yes, we want to have backwards compatibility of what we already have. We have message queue or event queue. All these sorts of events, they're generating events, and we're putting them into the queue. And if you're implementing that yourself, you can take any open source implementation of the queue. It could be MQP based, like RabbitMQ or ActiveMQ. It could be Kafka. So whatever you choose. And we have a diagnoser. And diagnoser is the thing which actually makes a decision on which event what to do. and we have specifications database. And it's not database as in MySQL, it's just database which describes on which events what to do. And then when diagnoser makes a decision, it puts that into the scheduler. The scheduler, knowing the whole state of the system, it knows the priority of all tasks we need to execute, and based on that, it sends that to the worker which are actually executing the action. And very important part of that all steps are logged and audited. So if something breaks, and auto remediation can also break, and we want to walk through all decisions from all steps which are made before. And here's a quick example. As we're working on storage team, we're operating on lots of MySQL databases. And in MySQL, we have replication, we have master slave. Sometimes your slave can break, and it could be like hardware error, like your disk went down, or kernel panicked, or even more painful, your rack is down because you have power outage, or your whole data center is down. So what we're doing, we're finding a new machine. And as Karoly already mentioned, we're treating our own hardware as a cloud. We're finding a new machine, and we're allocating this machine and making a clone. We're actually copying from one of our healthy slaves. We're copying data to the new slave. And after that, we're adding new slave into production. And after that, we are free to do. Production is fixed. We are removing the slave from production and sending that back to repair. Easy. Example number 2, MySQL master failure. So all steps they're not different from slave failure, except first step. We need to find a healthy slave and promote that to be master. And golden rule of software engineering, you're not repeating yourself, and we don't want to repeat ourselves, so that's why we have hierarchical state machines. So one of your state machines can include another as one of the states and the steps. So example number 3, kernel upgrades. What is a kernel upgrade? It's usually just maintenance. You're just upgrading to a new kernel version. You have simple steps like you're allocating a new machine. It's not intrusive. You're just upgrading kernel to required one. Just adding back to the production, removing the machine with old kernel from production. But that's actually the place where scheduler is useful, because maintenance is lower priority than fixing production, and scheduler can schedule fixing production before doing any sort of maintenance. And final example is verifying data consistency. We're really cautious, extra cautious about what we are doing and how we're storing data. And we're usually running, like every day, we're checking that MySQL replication works, even if it doesn't have bugs, but we're just extra cautious. And it also has just simple steps. We're cloning a new slave. We're stopping at a predefined checkpoint, running checks. We don't need that to add that into the production at all. We running like reporting result on verification and relocating that slave. Easy. And there the thing where synchronization is useful. Because this step is completely intrusive, we're not touching production at all, these data consistency verifications can run fully in background. And basically that's it. The point of our presentation is that be extra cautious. Don't trust anything. Thank you.
Thank you very much for this. So it's time for questions. Who would like to start? Hugo.
Do you inject failures intentionally on your infrastructure?
That's a good question. And actually, yes. We are running procedures called DIRTs. DIRT is just a acronym for Disaster Recovery Test. We're just randomly, every week, on some random day, we call these chaos days, we're just switching off rec, or 2, or 3. And it actually helps us to find lots of bugs. And it actually helps us to improve our infrastructure.
One addition to that is event is not necessarily a failure. So anything can be an event, and even if you don't react on it, since the event bus is not really something that is going somewhere, so you just take the message. We actually produce much more event than we react to. So it's more of a, there's a whole bunch of stuff, and we decide what to react on.
Okay. David.
Obviously, there's a recovery time. What do you do if a recovery time has not been met? So if it takes you too long for your FSM to recover from a situation, like a database clone.
Just make them redundant. Like, don't put eggs into the one basket.
Switch over immediately.
Well, I mean, a hypothetical situation, the machine that you thought was healthy was installed as a clone, and then you start replicating to it and it fails. Is this one of the situations you go to?
Yeah. I would ask you, why did you think it was healthy?
There was no indication prior.
Exactly. So your monitoring was wrong.
Don't take it, man. You and me out there. $50 in him.
Then what
Actually,
do
no.
you monitor? What do you monitor on the machines?
Everything. Almost.
Well,
So,
here's a hypothetical. So I was running database servers, and they have ECC memory. I'm handling it. It's all what you're supposed to do. And it's only when the load on the machine picked up and the machine got warm in a particular data center that I started triggering ECC memory errors. Now this happens halfway through a recovery. I'm curious what you do there where you end up with a failure, like I said, that was unknown. Your unknown. How do you handle that?
so we just had an issue one day when we arrived on a Sunday. Actually, we went to lunch, and in the car we had to stop on the side, and we fixed on the road. But yeah, it was sort of like the situation is that the master died, the slave wasn't able to pick up, but still the system is redundant enough, so it didn't produce user error. So yes, it can happen, but the idea is that you build everything, not just the database. So the database may have an availability dip, so we may lose, and again, remember that we are heavily sharded, right? So even if one shard goes down, that means that very small portion will actually notice it. And even they won't notice it because everything has the failure mechanism built in to retry or go to somewhere else for the data. So in this particular situation, if this goes down, then the client is smart enough to, okay, this one is not healthy, I go to this one. And it can just completely switch because we store every data more than once. So it's not a single replication chain that holds the data. The client recognizes that it's bad, and then it goes. So it's not just on us, of course, it's the whole company has to cooperate in a nice way that each of us can handle the other's errors.
And answering about ECC errors, we're constantly logging and analyzing kernel debug messages. And in case of ECC, we're not thinking to send them to repair.
Okay. Any other questions? So I have one question. So, of course, we all dream to have completely automatized recoveries in the computing centers and so on. But here, so this is an interesting problem, but there's also, I think, an interesting meta problem, which is how do you make sure that your monitoring and failure recovery system does not fail? So, and in principle, the very direct and precise question is, for example, if you are running the same network for your system and for the system that is supposed to fix the system.
So my answer to that is, and of course that's an ideal situation, which is hard to, but ideally most of the things that you do you don't need to be centralized. So many of the things can be done on the local space, right? So yes, you can have a central point which can fail, but you can have a backup for it. You can also treat that as I'm failed, somebody has to take over. I don't know, you can come up with a good example, but many of the things that a slave is broken, the situation can handle in the cluster itself. So if you have the right locking mechanism in your system, and you can have a lock on the scope of the cluster, so you make sure that you don't interfere with other operations in the cluster, then the cluster can make the decision itself that I need to do something with that slave. So you don't put, again, the same thing. You don't put all your eggs in one basket, and you try to distribute it enough. So each system is healthy enough to recover themselves.
Okay, thank you. Okay, any last question from someone? Okay, so thank you very much, guys.